Hi, good morning. Welcome to the talk. So quick show of hands, who here has used Flask before? Okay, and then who's used TensorFlow before? Okay, fewer people. So quick overview. Flask is a lightweight web framework written in Python, and there was a talk yesterday by the developer, Armin Ronischer. And it's lightweight in terms of you build what you need, so you can write more code or less code depending on what you want. This is compared to a more batteries included framework like Django, which includes more code, and you can rather than write more code, you can just choose which modules you want and configure them. And TensorFlow is a machine learning framework, which our previous presenter, Arpin, just spoke about. And it's written in C++, but it has a Python interface, and it was developed by Google and released just last November, so it's pretty new. So our stack today, which we're going to talk about, is Flask, which we'll have running on Heroku with Unicorn and Nginx. Flask WTF forms, which we use to take the input into our Flask app. We use pandas for some data manipulation. So pandas is a data analysis library. And we're using TensorFlow, of course, and Bato is a Python library for accessing Amazon Web Services. And in this case, we're using it for S3 for storing the TensorFlow models, which I'll discuss. So this is a quick overview of machine learning. And in this case, we're talking about supervised learning. So there are two main steps which we want to run on our Flask app. So we want to do a training step where we take training features and labels and feed them into our training process. And this will generate, through training, the trained TensorFlow model. So using this TensorFlow machine learning model, we can then run prediction. So on the right side, you can see we have the test features as input. So this is a different set of features than the previous training features. And we feed these into the trained TensorFlow model, and then it comes out with the predicted labels, as you can see on the right. So here's an architecture view. We'll have the client, which is probably going to be the data scientist on their web browser, talking to the Flask server. On the Flask server, we're running TensorFlow. We're going to run the training process on the input from the data from the client, and then generate the TensorFlow model and save it to our database. And in this case, it'll be AWS S3 as our data store. And then, so the TensorFlow model, after we save it to the database, we want to serve it to other we want to reuse it, so that's why we're saving to the database. And so we might have multiple Flask servers and many users. So for the users of our website, we want to take the TensorFlow model, load it into these Flask servers, which are running TensorFlow, and generate predictions based on the client data. So for each user, we might use the same model or different models to generate predictions for their input. So here's the Flask WTF forms form. I'm not going to go too much into detail. I just want to mainly point out this file field, which is how we take in the training input data. So this includes the features and the labels. So this is the input that the data scientists would use to feed in and train the model. And there's learning rate, batch size, and model name are other input fields. And so on our train method, this is the one with the a lot of the code. We have, this is on the top you can see this @app.route. This is a Flask decorator, which tells Flask that when a user goes to the train /train URL, with HTTP GET or POST requests, then it should call this method the upload method. So the first thing we do is create this training data form and check that the form data is valid. So this basically checks, as you can see here, there's a file field, decimal field. This will check that the input is of the right type and is valid. And so then we take these input fields from the form.model name, learning rate, batch size, and store them as variables locally and pass them on in the myModel.train. And we're also taking the file, saving it locally. So we have the form.trainingdata.data.save, and reading it in as a pandas data frame. So this pd.readcsv reads it in as a data frame, which is essentially it's a two-dimensional matrix of the data. And so we take the data frame and pass it to myModel.train. And David will go more into what this training method does in his part of the presentation. So the prediction form is basically where we just take some prediction data. And so this is a separate input where we only need to take one sample at a time. And so this sample of this set of features would come from other users of the app. So we basically here I just wanted to show the values, and David again will talk about more about what these mean and how they're used later. So we have the separate form. So on the predict side, we have another app.route for this different URL /predict. And so if a user goes to this URL with the get or post request, then we'll call this method and create a test parameter form, which I just showed in the previous slide. And if the request is a post request, then we'll take the input data, generate this. I'm not showing all of the casting to floats of all the inputs, but we pass it in as a two-dimensional matrix here to myModel and call myModel.run on the input row, and we get the results. And we return the results to the user so they can see the results here in render template if it's a post request. And then otherwise, if it's not a post request, then we return the template without the results. And so here, again, I'm showing you saving. We need to also save the TensorFlow model to our database. You have a question? Oh, no? OK. So here is our saving to AWS S3 method. So basically what we want to do here is take the TensorFlow model, which we generated previously during the train method. And so we have a local file with the saved model. And we have a model name, which is basically will correspond to the name of the file we want to save in S3. So the first thing we do is set up AWS S3. So we have to have the access key and secret key and create this S3 connection. We call c.getBucket with the name Flask TensorFlow. So a bucket in S3 is basically, it's like a directory. And then the key in S3 is kind of like a file name or file path in the directory. So we need to have both the bucket and the key to tell Amazon where we're storing it. And so we call f equals open file name. So this is opening up our local TensorFlow model. And we call k set contents from file f, which basically is doing the upload of our local file up to S3. And then on the other side, we have to get the model after it's saved so if we have other servers which are running prediction, then we need to get the model from S3 and load it back into TensorFlow to run. So here's our load from S3 file. Again, we have to do setup. So the first AWS access key, secret key, connection, getting the bucket are the same. But in this case, instead of instead of creating a new key, we have to get an existing key from S3 because we want to get a model which has already been uploaded. So we set the key to the model name, and we create a file for writing to locally, so we can copy the file from S3 to our local directory to be loaded into TensorFlow. And so the last part for setting up our web server is we have to actually deploy. So in this case, we're using Heroku, and it's very simple to set up. Heroku is basically a service, a web provider, which will host your app for you. And so what we need to do is pretty straightforward from our repository. We set up the Heroku, we install the Heroku command line interface, which you can do on this URL. We create this proc file, which just includes one line. This line tells Heroku what command to run after, basically when it wants to start up your app. So in this case, we're running Unicorn with main app. So our Flask app is in this main.py file. And Unicorn is basically a app which routes the HTTP request to our Flask app, and it's written in Python. And then to deploy, to actually push our code to Heroku and run it, we have to create an app on Heroku, so we call Heroku create. This creates the Flask TensorFlow app on Heroku, and then we push our code using git push Heroku headmaster. And so for more information on the git setup for Heroku, you can go to this URL. And so next, David will give the nitty-gritty details of TensorFlow. So.
Okay, thank you, Kendall. So what is TensorFlow? This was developed by the Google Brain team. It's graph-based. And the nodes, these are operations. And where the edges are, these are multidimensional arrays called tensors. So the edges, they'll hold the data, such as the training data, the test data. And the operations, that's where you're manipulating the data during the modeling process. In TensorFlow, all the operations are done outside of Python in a TensorFlow session. And Arpan talked about this a little bit. TensorFlow uses placeholders and variables to store the information that it needs for the modeling process. Placeholders store the fixed input, such as the features and labels, the training set, and the test set. In variables, this store variable input, such as the weights and biases, things that are going to change during the modeling process, and they're going to get tuned. So why might TensorFlow be better than other machine learning libraries out there? Well, for one thing, it's portable. TensorFlow can be used on something as small as a cell phone, a mobile device, all the way to distributed computing using GPUs. It also, as Arpan demonstrated, it includes a visualization tool called TensorBoard, which allows you to be able to view your model and assess it. All events are logged, and those logging of the events, that's what gets passed to TensorBoard during the modeling process. And it also includes checkpoints. So you can define checkpoints in your code, and you can stop the model at that checkpoint, can evaluate the model, and then you can continue the modeling process. And it's also open source. So what is a tensor? There are vectors, which are one-dimensional, one way to group data, and matrices, which are two-dimensional. And tensors include both vectors and matrices, but can go to higher dimensions, 3 or more dimensions. And TensorFlow, that's what TensorFlow uses to store data. The data set that we used for this demonstration is the wine quality data set taken from the UCI machine learning repository. I have the link here. This includes chemical properties for wine of the Portuguese Vinho Verde variant. The properties are chemical properties, and I list a few here: volatile acidity, citric acid, residual sugar, and etc. These are the features. The labels for this model are the quality scores. So these are the subjective quality between 0 and 10, where 0 is a bad wine and 10 is a good wine. The features, they don't include things such as the grape type and the brand name or price. Before the modeling process, we need to clean the data. A couple of things to consider, or one thing to consider, are outliers. These are features with extreme values. And for purposes of this demonstration, we're using a simple assumption to say any values that have a greater than 5 sigma from the mean of that distribution is an outlier. And we set those values to the mean of that distribution. And I show the function here at the bottom that I used to be able to correct for outliers. Another thing to consider when you're modeling data is collinearity. This can occur in a data set like the wine quality data set, where you have a lot of different features that might be linearly related to each other. In that case, if two features are linearly related to each other, then one's going to change as the other changes as well. And so it's going to lead to redundant information, and it won't be good for the modeling process. So we decided to remove fixed acidity, which shows collinearity with pH and density. Now we're going to group the data into 2 different groups just to predict whether wine is good or bad. We're defining good wine as having a quality score of between 7 and 8, and a bad wine of having a quality score of between 4 and 5. When you're doing a categorical model in TensorFlow, one thing that you also have to consider is the format of how you express those variables in TensorFlow. And you have to use something called a onehot vector. This is a vector that consists of zeros and ones. The length of the vector is equal to the number of unique labels that you have in your data set. In this case, we have 2 labels, good and bad. So each vector has a length of 2. So bad is a vector of 1 in the 0 spot, and 0 in the 1 spot. Good has a 0 in the 1 spot, in 0 spot, and 1 in the 1 spot. In this function at the bottom, this is where we are converting the labels to onehot vectors so that we can pass that to TensorFlow during the modeling process. Now we split the data set into the training set and the test set. In this case, we're going to use 90% of the data to train on and 10% of the data to test on. The model we chose to use is called softmax regression. This is similar to linear regression, a little more complicated, but it's a good way to algorithm for categorical data. It's a way of adding up the evidence that one feature is of a specific category. So the weights are given a negative weight if it's not of that category, if it's not good or bad. And positive weights are given if it is of that category. And here at the bottom, this is how softmax regression. So this is the softmax regression model. And you can see the weights and biases. Those are in TensorFlow variables. So that's something we're going to tune during the modeling process. I'm also giving it a name so that when we save the model, that we know that that variable refers to the weight if it has a W, or a B if it refers to the bias. We then set up the model at the bottom. So that's what the y equals this TensorFlow softmax regression model. So there you can see we're using doing a multiplication, matrix multiplication of the features, the training features with the weights, and then adding the biases, similar to what Arpan talked about in his talk. And then we're going to return here at the end, we're going to return the model and the weights and the biases. So now this sets everything up for TensorFlow. Next thing to consider is the cost function. This is to be able to assess how good of a fit your model is to the data. In this case, we're using cross-entropy function, which is defined here. Y prime, these are the training labels, and Y is the model that we defined in the previous slide. Now we need a way of being able to fit the model to the data. And for that, we're going to use the optimization function. So this is basically a way to progressively change the model until you get to the best fit. And that's the minimum value where it has the best fit. And that's where you would use an optimization function. In this case, we're using gradient descent. A couple of things to consider when you're training the model is what learning rate that you want to use. If this is how fast you want the model to search for the minimum value. If the learning rate is too large, then you might overshoot the minimum, and so you'll never find what the best fit is. If it's too small, then it could take forever to find out the minimum value. And this is something that when you're modeling the data that you just have to tweak to find out what the best value is. So here at the bottom, I'm showing more code. The first you see is the placeholder, this for y prime. So this is going to store the placeholder for the training labels. Then I define the cost function using the reduce mean. And so I'm passing in there the training labels and the model, which is defined earlier. And the next step is the optimizer. That's where we're defining it's going to be gradient descent optimizer. TensorFlow has a lot of different optimizers, but this is just one of them. Then the learning rate. And then at the end, we're saying that we want it to minimize the cost, which we defined in the previous line. And so that's the optimization step. And then the next line, this is the line to be able to store what the correct predictions are. So this is going to compare our model to the training labels. Remember, the model during the process, the model is going to keep changing and updating as it's improving during the training process. And then the last, defining a variable to specify what the accuracy is, the final accuracy of the model. Now we're ready to train the model. Training is done using batches and epochs. So batches, this is when you separate the training data into separate chunks. And you train the model on each chunk. And each time you train it, you improve the model. You tweak it a little bit using the optimization function. And then you pass that on to the next chunk. You keep repeating that process as you keep improving the model. And you can go through the whole training set. But another thing you can do is you can repeat that whole process over and over and over again. And each time you repeat it, it's called an epoch. And so those epochs are how many times you want to repeat the training step. Okay. Some of you asked about how to saving the model. First, you need to define a function where you're going to save the variables. So I have this. Here, we're defining a variable, tf.train.saver. And this is going to save the variables that are that we're changing during the modeling process. We then need to initialize the variables. So that's the next step. Now we're going to start a TensorFlow session. And here's the training step. So at the top, we're initializing TensorFlow session. We also have a list here. This is where the training steps are going to be saved, and going to be out for. We want to save the training steps so we can output it to the web page on Flask, using Flask. And then the next step, the first loop, this is the epochs. And so we're going to loop through all the training steps 100 times, so 100 epochs. And the second for loop, this is where we're looping through each batch. So the line before that, defining the number of batches that we're going to use. And then loop through it. And then you have the optimizer, the average cost. After 10 epochs, we're going to print what the cost is, so we can monitor the modeling of the data. And then we're going to store the model to a list, the modeling progress. So we're logging the steps, logging the modeling process. Are there any questions there? Finally, after we've trained the model, we want to print out what the final accuracy is. How well do we model the data? So that's this step here. So remember I defined before the accuracy variable. And so that here I'm passing in a dictionary. So it's taking the test data set, test features and labels, and passing that into the accuracy that we defined. And it will print out what accuracy it is, how accurate our model is. And then we'll log the accuracy. We'll just save that to the list for the web page. And then we'll save the model using a checkpoint file. So that's what this next step is doing here. So it's saving everything that we defined before as a checkpoint file, which we can access and open using the Flask app, and then display it or use it to be able to predict how good the wine is, if it's good or bad quality. And we're returning the list. This next step here, this is done in a separate file, and this is the main Flask web page. This is where we're going to start our TensorFlow session, and now we're going to load the saved data, load the saved model. And that's what we're doing in this with clause here. You can see, so it's loading it, and then the save.restore. So that's actually where it's going to restore. What that's saying is for that session that we defined, it's loading the checkpoint file. And then now we can use that to be able to do predictions. So now I'm going to switch and demonstrate the web page. So here's our wine quality tester. And first I'll show the test page. So here's the different values, input values. So let's enter some values here. So I'm just picking a wine that was of bad quality. We'll see how it does. Sorry, off by 1.
Didn't you say you removed fixed acidity from your model because it was collinear?
Oh, yeah, that's a good catch. I think that's a mistake. But yeah, okay. Thanks. Let's try this again. Okay, so there it prints. Okay, so that's a test page, but we also have a training page as well. So here we can load the CSV file. So again, we can specify the learning rate and the batch size, and a name for the model output. So now it shows the training parameters, and it lists the cost and the different epochs, and the final accuracy.
Did it train all that just now?
Yes.
You did 100 epochs in like a second there? How many examples do you have?
It's I think it's 4,000 lines, so it's not terribly big, but it's not like millions of rows. But yes, yeah. So, okay. Well, yeah. Thank you. Questions?
Yeah, a question?
You mentioned that the optimizer you used was a gradient descent optimizer. That's the only one I'm familiar with. Have you ever used any other optimizers? And do you have any experience with any of that?
That's the main one that I've used.
Yeah.
I know there's another. That's the main one I use, but I know there are many other ones. Another one, there's the atom optimizer. Sometimes think I have some improvements. I don't know what the different R's are, but yeah, there are quite a few.
Okay.
Yeah.
So the training part of this, how realistic is it to run your training on a server context? So if you're actually on more than one user, more than one server, and the training takes, like in this case, it's quick, but like multiple jobs
Yeah, that's a good question. So the question is, if you're training the model and many different users are training the model, how realistic is it? Yeah, I mean, it would depend on, I think your resources, but it's also something I think that if you're training the model, you want to be careful because you don't want people to be kind of stepping on each other's toes if you're trying to come up with the best model. So there might be conflicts there. In terms of doing it on the web, I mean, this showed it. All the inputs are just specified inputs, but then everything's being done in the back with TensorFlow. So I don't think time-wise it's not going to be a whole lot different.
Yeah, it does depend. I think the idea is with the model is we only have like one or a few users who are actually doing the training process, and it's not a continuous process. Or if it is continuous, it's like you're not doing many in parallel. So I think I showed in the example, so it'd probably just be like one data scientist in your team or a couple of them. And if you do need to scale up, so our example is built on just expecting one server for training. So if you need multiple servers for the training process, then Google has some examples, I think, with more distributed processes with TensorFlow. Yeah. Does that answer your question? Okay, cool.
Why did you throw out or basically set to the mean all the outliers? Is that just to make it more regular?
Right. So the choice of doing that was, in some cases, if you have features that for whatever reason it was a bad measurement, or just something about that wine that had their really extreme values. I mean, that's one reason I chose like 5 sigma. Then it could kind of tug your model in the wrong direction, and so that's why in this case decided to set those values equal to the mean, just to improve the model fitting. Thank you. So the question was here, I used the softmax regression, and how does that compare to other algorithms that are out there? There are other options as well. You can use logistic regression is another option for categorical data. So there are a few other options as well out there. I've even seen, I think, even like with the MNIST data set. But there you're dealing with data, which are images, but people have used like convolution neural network there. So there's... Mm-hmm.
So you define classes yourself essentially by a range of scores, right? Is there a gap in the scores that you thought there might have been like good and bad seem to be sort of far apart from each other? So
Right.
on like 5 to 7s, were those disregarded?
Yeah, that's a good question. So there's the quality scores of 6. You'll see that that's not here. This is the choice of doing this was more to be able to come up with distinct categories. This, I don't show it here, but when you look at the plots of the data, if you plot scatter plots of the different features, you can see that there's a lot of overlap. There's a lot of confusion. And with TensorFlow, you can resolve that confusion, but it can be pretty complicated. So for more purposes for this was just choosing these values to be able to help the model process and being able just to demonstrate using an interesting data set how you can use TensorFlow. Thank you. Mm-hmm. Oh. Yeah, no, that's a good question. So he's asking if each quality score has equal amounts of data. And the answer is no. There's more data in the average category and much fewer data in like the really excellent wines, the very poor wines. So that also makes it a little bit more complicated. You don't maybe have enough values for the really good wine, the really bad wine. So it's hard to kind of differentiate the different values. Good question.
Do you have an opinion on when it makes sense to use
Right. That's a good question. Yeah, I don't know softmax regression might be better if your data is more complicated. But specifically, I don't know if, I think it might be neat to try both logistic regression and softmax regression. But yeah, that's a good question.
Any other questions?
Cool. Yeah.
Great.
Thanks a lot. Yeah.
Thank you.